On today's episode of Performance Talks, we conclude our Cantrilogy as Bryan and I discuss complexity, constraints, and the importance of keeping things small and simple.
When I've written like low, high performance C, like pieces, like literally sat with a function for a week until you just can't get one more drop of performance out of that thing.
Yeah.
I then know that it's going to take me 2 weeks to comment it because I'm never going to be able to read that code again.
Yeah, and
You feel that way with Rust? Because the little Rust that I've done that I've like to make it more performant, I've actually looked back at it and been like, okay, this is actually a little more intuitive.
Yeah, I mean, so the thing about Rust is that the primitives themselves are very high performing. So I had this experience where I'd written this thing in C. I rewrote it in Rust, kind of one of my first experiences with Rust. I was trying to do it in a clever way, and Rust, in its way, was telling me that was not going to work, and that Rust was just abusing me. And I finally just had an emotional breakdown and be like, now actually I just want to get it to compile. And I've stopped caring about the performance. So I'm not going to do it a fast way. I'm going to do it a dumb way. And I did it in the dumbest possible way. And it outperformed my C.
But that's, to me, the essence of how a language should work.
Yes.
You should.
Yeah.
And again, I'm obviously the child of my upbringing, but Arthur Whitney's relentless 35-year march towards the fastest, highest performance code should be the shortest. We think about that as terseness, but what he's really saying is like the simplest thing that you can imagine, the easiest way to do it, that should be the fastest way. And if it isn't, that's actually a problem in the language, and I will go fix it.
Yeah, I think that there's definitely truth to that. Because I was so flummoxed by this that I spent quite a bit of time understanding why it was almost like dispiriting. Like, I didn't view that as a reflection on Rust. I viewed that as a reflection on my own C.
Now, here's an interesting, so you have a piece, so you have a Rust binary that is running faster and you don't know why.
Right. Well,
What tool did you reach for?
So
to go figure that out.
That's all compute bound.
Yep.
So the first question I actually had is let's look at this program in terms of the machine. So, and this is atypical, I think, for me. Normally I'm dealing with more complicated systems programs where I don't have this luxury, but this is 100% compute bound. So tell me about what we're doing with respect to memory, cache, instructions per clock. What is the CPU doing? And discovered that the Rust version had much better memory behavior, and much higher. It was funny that the number of instructions retired was basically identical, which was, as it turns out, a coincidence, or within 1% of one another. But the Rust instructions were executing much faster because the memory performance was much better. The reason the memory performance was much better was because the short version is I was using a B tree in Rust because that's the only choice you have. I was not using a B tree in C because a B tree in C is gnarly, and you would only implement a B tree in C because you absolutely had to, not because you.
And I'm sure that you, like me, like every other C programmer, has that B tree header file, that you wrote or stole and you have no idea how it works.
So with a B tree, my go-to with C has always been an AVL tree because I know I can embed a node in a structure and immediately go. And a B tree is nasty because the interface is so nasty. The reason a B tree is so hard to implement in C is that a B tree is going to the B tree is like, hey, you know what? I'm going to move shit around, by the way. So you can give me this thing, but definitely do not get comfortable about where it is physically located, because that's what I do. I move shit around. That's my whole reason for being, is moving shit around. And C does not like you doing that. It's very hard to, it's possible, but it's hard to do that in an interface, especially for kind of arbitrary objects. You'd be like, all right, well, here's an integer. Well, okay, fine. But now it's like, okay, now I've got a super complicated structure that, by the way, a bunch of other things have pointers to this thing. It's like, no, you can't fucking move that shit around. That's just no, please don't. And so ultimately, that is why Rust was faster, was because there is no balanced binary tree structure in Rust. It's all B trees.
But you didn't use the language to debug the language. You used your tooling that you're used to.
Yeah, I used the CPU's view of reality, and then did ultimately couple that with dtrace to figure out, okay, especially to answer some more, because I as I started looking at the performance over a range of inputs, I saw a more complicated pattern. So trying to figure out exactly what was going on there, and discovered that again, it was basically the B-tree implementation that was just like, and I kind of wrote this all up, and this is like, what, a year and a half ago that I posted this. And a bunch of people were like, well, did you write it with Clang? It's like, okay, can you not read? Like, do you think Clang? Yeah. Oh yeah. Clang is going to change the
compiler's smart, but it's not that smart. It's not smart enough to be like, oh, hold on, I'm just going to swap this code out for this entirely different algorithm.
Right, I've got a whole different way of writing this that's actually a lot better. A little error prone though, so good luck. But it was eye opening, and now I feel like that was like one of my first moments where like, oh shit, like this language is actually. Because I was actually at the point, I mean, I don't really talk on this, but like when I went into Rust in the summer of 2018, it was out of despair. It was like, I do not know what my path forward is. Like, if it's not Rust, I don't know what it is. Like,
what would have been wrong with writing C for 20 more years?
Well, that's what it would have been. I would have been like, I would be writing C for 20 more years. And that was going to be like, I'm going to embrace that. Like, that will be like, that's fine. I will not use power tools. I will use my own hand tools, and I will make the world's most beautiful Amish software furniture. And that's fine. Like, I'm actually cool with that. Like that's like, I was like coming to grips with basically living without motor vehicles in rural Pennsylvania, making my bespoke software furniture. Fine. And so, but Rust was a relief in that you're like, okay, actually, this is interesting. It is a replacement for C. And then what's been especially interesting in the last couple of months is as we've gone down the stack, it's like, okay, I mean, obviously like Oxide, tip of the hat to Rust, but I also didn't want to assume Rust everywhere. But as we've gotten into these embedded use cases and up the stack, you begin to realize like, it's not perfect, but it's pretty goddamn good. And
I'm always like, anytime something fits in lots and lots and lots of places, I'm like, it's either really, really great, or like you're going to end up like Go, or like JavaScript, right? Where like, don't get me wrong, JavaScript in the browser, I mean, it is what it is. Node, I mean, JavaScript doesn't belong there. Like, it doesn't, like, we have it there. We run a lot of Node.
I know, I tried. I did try.
But she really shouldn't be there. I mean, it's putting a square peg in a round hole. But with Rust, it's like we can. So it's interesting enough where we use Rust today, and where I see us using Rust over the next 2 years is in the front end, is in the browser.
Yeah, right.
Because the WASM target is so good.
It is good.
So I've done some C to WASM automated generation, and it just like, I mean, it just doesn't work. Or like it works and it's like, ooh. And again, reading WASM is kind of like, it's like the paint by numbers equivalent of reading assembler. So you're like, actually it's like, you know what it looks like? It looks like Lisp, because it is like Lisp.
Right.
But the Rust, the stuff that comes out of Rust is fantastic. We did an XX hash. Took the rest and did an XX hash implementation. The WASM comes out and it's
tight. Exactly.
Really tight. Really tight, really small. And interestingly enough, the WASM on the front end on the browser will run faster for a couple of reasons. One, you're shipping binary, which is always nice, but it's streaming compilation. And then once it's done, it's done. Yeah. So the only place where you got to pay this penalty is that barrier between the WASM kind of execution context and the JavaScript. But crossing that barrier gets cheaper and cheaper every day. But yeah, I can totally see doing front end websites, I can actually see Rust being the language that generates WASM to do that.
Yeah.
Rather than JavaScript, which
and at the same time, I'm telling you with the same amount of conviction that we are running it on SoC parts that have, maybe have 600K of RAM.
And so you clearly work with the Rust team how big is the core Rust team? Because this kind of gets into like another interesting pet peeve I've had the last few months, which is team size.
Yeah.
And, so the core Rust team is, I don't know.
How big is that?
10 people, 50 people? I mean, in the very beginning, it's probably just a handful of people, right?
Yeah, I don't actually know.
Yeah.
I don't know. I mean, it's an interesting model because it's like, there's not a real Rob Pike equivalent.
Right.
It's not it's not a benevolent dictator for life kind of model. It's very community driven. There's a lot of, but it's thoughtful. I do think that, and Steve Klabnik, who actually just recently joined us at Oxide, has got a great presentation on this, on Rust's values. I do think Rust knows what its values are. And I think that this has been very helpful to allow it to scale in a way that doesn't sacrifice those values.
And so, Rust still feels like a small community with lots of packages that you can bring into the world. Like cargo and all that stuff feels like a big land of, which is very healthy. I'm all for that. That's like my favorite part of the open source community is being like, oh, I want to experiment with this, wacky algorithm, but I don't feel like writing it. Can I just pull this in and play with it? But like the core of the Rust compiler, like that community feels fairly small, and like language direction feels fairly small. And I think,
and that's a good thing. I think that's
And we've talked about this, like big communities versus little communities. But how do you translate that? So, joint engineering was not a big engineering team, considering the size of the problem to be tackled. And Oxide
is maybe more extreme.
Is probably more extreme.
Yeah, it actually is more extreme. So we've got 17 and arguably 8 different startups.
Right.
We are rack scale machine trying to do a lot in there. It's a lot. And yeah, it's too much, really. But I've always been a believer in the power of a small, empowered, focused team.
Now, where does that, because that's been my mantra forever, for my entire career, and it's very simple, right? I want 2 things, and I want them in equal amounts. I want the least number of best people. And like, that's it. And a lot of that, again, comes with that idea of like, I want the systems that we're running and deploying and operating to be understood as deep as can possibly be done, so that there are no surprises. And I find that the deeper you understand something, operationally and development-wise, like everything just gets easier. But does that break at some point? Do you eventually need to have, because you've got your VC that's, wants you to go have 50. I feel like staff numbers are kind of like Kubernetes pods numbers. Like it's this thing that you're proud of, when I actually feel like you should be the opposite.
You should be opposite. Yeah. And I think that fortunately, we all have the disposition, in part because we're all veterans. Steve, Jess, and I are all veterans, that we are trying to do the most with the least number of people. There's a challenge because you also don't want to have a team that feels under-resourced, where it feels like being stretched beyond the breaking point. And, it is a balancing act. But yeah, we have biased ourselves very heavily on keeping the team small. And then you also want to keep the team filled with people who do well when things aren't very structured, because you want people to be able to meaningfully find work that needs to be done, gravitate to it, and do that work. And that's also a real challenge. And also, I mean, that's also the phase of the company we're at. I don't know, what does Oxide look like with 1,000 employees? I've got no idea. We'll see how much of this scales or doesn't.
I mean, Sun's OS engineering team, which I know I'm talking about that like that was one product, but it's not one product, but it's certainly one product line. That engineering team at size was what? 500 people?
Yeah.
600 people?
Yeah. So 500.
And then how many of those people actually did the work?
A small
100?
Yeah, a small
100?
And a smaller number. And then also, like, even it's not that people weren't necessarily doing work, but of how much of that work was like actually you get, once an organization gets large enough, it will find work for itself. So in other words, you can have a lot of people doing work, but the question is, like, is that actually work that makes sense? And you do hear about these projects that are got, there's a project at a hyperscaler that I'm not going to name that we're definitely hiring people out of, that I assumed had, like, I don't know, 15 people on it. It's like, no, it has 450. You're like, what? And we're talking, like, in some ways, it's the worst possible scenario, because like 450 bright, motivated people on a pond that should only fit like 15, they'll devour one another. Like that will, I don't care how that group, even if they are all well-intentioned, that will divide into civil war.
Yeah. And I think once you get to that organizational size, it's almost impossible to clean it up. Like, my buddy works at Agilent, which used to be a part of Hewlett Packard. And he said something to me that I think about all the time. He said, an organization will act as it did at its largest moment in time.
Ooh, yeah.
And that, the ability to, like, right size an engineering team when it's become wrong sized is kind of like restarting an economy that's gone off the rails. Like, it's a lot harder to just keep it on the rails. It's a lot harder to just keep it as small and uncomplicated as possible. And I think this is, again, like, is this a result of how we grew up when we had small machines and not a lot of resources and not a lot of people who were in our industry, which I think it's great right now that I could throw a baseball and hit 5 programmers. I'm not going to be able to hit 5 engineers, but I could hit 5 programmers. But I think that minimalism is really important.
It is.
So
I do think that and this actually kind of brings us back to where we started in terms of performance, because constraints give rise to creativity.
Absolutely.
And when we remove those constraints, we end up with artifacts that aren't as good. So those constraints can be around size, around latency, around throughput, around people, but those constraints give. I would say that the exception to that would be a constraint around time, in that the more immediately you want to ship something, that's not going to yield creativity necessarily. I mean, I guess it can, but I think that often yields sloppiness. So that's, as an industry, I wish we would remove the time constraint a little bit and not talk so much about developer velocity, which makes a software engineer sound like a projectile, and instead put in constraints around complexity, around performance, around size, around these other things that actually yield better artifacts.
Innovation per employee, something like that, like performance per watt.
Yeah. And
so the Cantrillian management tip is, you can't manage what you can't measure, and you can't innovate what you don't restrain.
Yeah, I guess it is.
Yeah.
That you need to, that constraints are, we have a complicated relationship with constraints, but it is out of those constraints that we do our best work, even though it can feel most frustrating at the moment.
Yeah, man, I think that's a perfect place to end this. That's what we should all go forth and do.
Exactly. So, go forth and constrain ourselves.
Yeah, and shoot complexity like Indiana Jones with your revolver, which is still one of my favorite metaphors of all time.
It really is. It's a classic.
All right, well, with that, Bryan, always good to talk to you.
Thanks for having me, Jack. Always good to talk with you.
Tune in next week for another episode of Performance Talks, and be sure to subscribe to stay up to date on our latest interviews.